Okay, we're going to be trying to find some points of discontinuity, if there is any, of the function f of x here is x minus 3 over x squared minus 9, and then this integer function here. I think the greatest integer function, also known as the floor function, but we'll talk about that when we get there. Okay, so this is what we got. We got x minus 3 over x squared minus 9. Now, what number can I plug into the denominator and get 0? And that's where we're going to be trying to start to find any points of discontinuity. And if I factor the denominator, we see that we get x minus 3 and x plus 3. And since there's an x minus 3 up here in the numerator, if I were to plug 3 into the numerator, we would get 0. And if I plug 3 into the denominator, we also get 0. So we can see right there that there is a point of discontinuity at x equals 3. Now, so the first thing we want to do is we want to find the limit as x approaches 3, and I'm claiming that this limit is 1/6. So remember, to be able to find this, first thing you want to do is factor this out, cancel terms out, get a new limit, and then evaluate it from there, doing the direct substitution, plugging 3 directly in, and we get 1/6. So as you can see here that the limit does exist at x equals 3, but when we evaluate f of 3, we get 0, 0, which means this is undefined. So this is where it fails, right here. So we know that it's not continuous at x equals 3, but it is discontinuous at as x equals 3. Now there was another x value that we should have checked, and that what happens when we plug negative 3 into this? Well, we end up getting 0 in the denominator. So now we're going to check negative 3. So that means we must take the limit as x approaches negative 3, and I'm saying that it does not exist. So remember, we factored cancel terms out. We got down to 1 over x plus 3. We plug negative 3 in, and we get 0 in the denominator. So that tells me that this limit does not exist. So we know that it's definitely not continuous at x equals negative 3. But let's take a look at the graph first before I start talking about this. So here's our graph. Here's negative 3 on the x-axis. Now we can just look tell by looking at the graph as we come in from the right-hand side approaching negative 3. What's happening to my graph? It's going up to positive infinity. All right. And coming in from the left-hand side, the graph is going down to negative infinity. So we know that it is not continuous. Now over here, the first part that we looked at when x is equal to 3, this is just a hole in the graph right here, even though I don't have it labeled right here. But remember, there was just a hole in the graph here at x equals 3. So this is how we write it out, right? As x approaches negative 3 coming in from the left, we say that, now this is not an equal sign, this is just saying, hey look, the limit is going to negative infinity. Remember that our limit's always equal to a real number. Now you may see in textbooks and so forth, they may just write equals here to negative infinity, but remember that the limit really is not equal to negative infinity, it just tells us the direction the graph is going in. And then of course coming in at negative 3 from the right hand side, remember it was going to positive infinity. Okay, but let's just go ahead and work our way on down this. Let's f of negative 3, and that's obviously undefined. And remember, the very last step was, are both these equal? And obviously not, right? Obviously not. Now we say that this is discontinuous at x equals negative 3, and this is known as a non-removable discontinuity, and it's because of that vertical asymptote. Now in that first part, it was discontinuous at x equals 3, and this is a removable discontinuity because it is a hole in the graph. So think of a point in the graph as being removed. Alright, we're going to be looking at this special kind of function here, the greatest integer function or the floor function. Anyway, so this is the graph of this function. Now the way this function works here is if I take a number, for example, a number less than 1, greater than or equal to 0, like for example 0.2, and if I plug 0.2 in here, it's going to, I guess, round it down to 0. It's going to round it down to 0. Now if I plugged in something like 0.99999 into this, right, so it's rounding it down to 0. Now if I plug 1 in to this right here, okay, it's going to keep it at 1, as you can see here, keeping it at 1. So that's the reason this is a hole in the graph and this is a solid dot. So when we plug 1 in, we get 1 out. Now for example, let's say we went to 1.3, maybe somewhere here on the graph, and we plugged it in, so 1.3 is going to keep it at 1. It's going to keep it at 1. So it's kind of like rounding down. I mean, if you said 1.7, right, it's still going to keep it at 1. But let's just kind of look at the continuity of this graph here. That's kind of what we're talking about. You can see here that this function is continuous, right, in here, but then it's broken at 1, it's discontinuous at 0, it's discontinuous at 2, so it's discontinuous at all the integers. Alright, discontinuous at 3. And I just want to kind of show it as x approaches, for example, 2. So we're just going to kind of show it on paper. So remember the procedures that we take. First thing we're going to do, let's look at the limit as x approaches 2 of our function, and of course it doesn't exist, because if we look at 2 coming in from the left hand side, it was 1. Coming in from the right hand side, it's 2. Right, so here's 2 on the x-axis. Coming in from the left hand side, okay, our function stays constant. As I get closer and closer to 2 from the left, right, it remains 1. And then coming in from the right hand side, it's staying constant, and it's going to be 2. So because coming in from the left and coming in from the right are 2 different numbers, right, the limit doesn't exist. Of course, we can easily look at that just by looking at the graph because it's broken here. But what about f of 2? So we take 2, we plug it into the function. Well, it's undefined here, but if we go straight up where the solid black dot is, okay, come straight across, this would be 2. So we say that it's discontinuous at x equals 2, and because the graph is broken, this is known as a non-removable discontinuity. Now I should say here that I should have labeled this at f of 2 also, and then set them both equal like I've been doing, but it seemed like for some reason I didn't do that in this problem, but hopefully you understand. Let's look at another point on the x-axis. Let's look at when x approaches 1.5, or I should say, is this graph continuous at 1.5? Well, we take the limit as x approaches 1.5, and of course remember we're rounding down again, and so we just get to 1. So that exists, happens to be a number, and then we need to do this part. Now remember I skipped this part here, writing this out in the last problem, but I actually wrote it in here. But we have f of 1.5, right, and so we plug 1.5 in, and we also get 1. So since these are both equal, right, they both exist and they're both equal, then we can say that this is continuous at x equals 1.5. But it's obvious when you just look at the graph. But sometimes we just don't have the graphs to look at. So we just got to trust the math.